A cycloalkane contains carbons that are arranged in a ring. Cyclopropane has 3 carbons. Cyclobutane is 4 carbons. From that bute, so we have that prop, and the bute tells us how many carbons there are. Cyclopentane has 5. And cyclohexane has 6. And notice that all of these names start with cyclo, which tells us it is cyclic. And there's a couple of different compounds here that we can see that naturally contain cyclic structures. Permethrin is in a flower, and also vitamin D is in milk. So cyclohexane can appear as a non-planar cyclohexane chair form, and you can kind of see the chair here, and we'll go into this in more detail later on. With these organic structures that have different cyclic structures within them, you want to keep in mind that having a cyclic structure isn't going to contribute to its water solubility. So neither of these compounds are water soluble. And that is because the ratio of carbons over the oxygen and nitrogen are not less than 4. When we're naming cycloalkanes, you're going to find the parent cycloalkane. Number of carbons in a ring is the parent. We add cyclo to it and then add the suffix ane to the parent name. We're going to name a number of the substituents beginning with 1, and it's going to have the lowest overall numbering. So for this ring, if I look at the bottom, I have 2 substituents at 1 and 3, so that's going to give it the lowest numbering. We wouldn't number it counterclockwise here because that wouldn't be the lowest overall numbering. So for naming this top structure up here, I have the choice of 1, 2, 3, or I could number it 1, 2, 3. The numbers in that case are both the same, but I'm going to give the alphabet the priority. So with the red numbering, I have 1-ethyl, 3-methyl cyclohexane, and that name is better than 1-methyl 3-ethyl. So we want to use the one that has the lowest alphabetical if the numbering is tied. So this one here, if there's only one substituent, it's assumed at 1. This is 1-methyl cyclohexane. If I have 4 groups coming off, this is 1-butyl cyclopentane. And down here we have 1,3-dimethyl cyclohexane. And this would be the same as the one we did up there. This is 1-ethyl 3-methyl cyclohexane. Okay, here's a couple more practice problems. This group here is a propyl. There's 3 carbons. This is 2, so this is an ethyl. Ethyl comes before propyl, so I will number clockwise here. 1-ethyl, 2-propyl cyclopentane. This is an ethyl again, also a propyl, but our numbering is different now. I'm going to start with 1 here again. This will be 3. So 1-ethyl, 3-propyl cyclopentane. With 2 groups on the same one, we are going to number that 1, and they'll each get their own number in the naming. So this is 1,1-dimethyl cyclohexane. Alkanes come up a lot in natural gas. It's 60 to 80% of natural gas is made up of methane. And then petroleum is a mixture of carbon-containing compounds that have 1 to 40 carbon atoms. And this crude mixture is refined by the boiling point. And we learned earlier that the more carbons that are in a chain, the higher the boiling point is. As you boil the mixture, it will go to different temperatures and get distilled off of here. So gasoline can be distilled between 20 to 200 degrees Celsius. And the longer chain carbons will be distilled at higher temperatures such as 350. So we get a barrel of crude oil, and it's composed of many different things. There can be products made from petroleum, and all of those oils get heated up and they go into the different boiling point vapor phases and get collected at different temperatures. Cattle farms in the US use manure digesters to convert animal waste into methane, which is biogas. That can be used to generate electricity. It's pumped into the oxygen-free tanks. The bacteria that are in the tanks can break down this organic material to form methane gas, which can be collected and combusted to make electricity. Any residue is compressed and used for fertilizer. So you can see the methane gas bubbles here. Alkanes have nonpolar carbon-carbon and carbon-hydrogen bonds. So the intermolecular forces they have are only weak ones. Alkanes tend to have low melting points and low boiling points. If they have more interactions, then they have higher boiling points. These are not very water soluble. And this can be problematic to animals. Often it poses a threat to birds if there is an oil spill. Feathers of regular birds are coated with natural oils. So if there's an oil spill, the petroleum oils can dissolve the bird's natural protection and get that coating all over their feathers, which is hard to remove. The boiling point for butane, which is 4 carbons, so BP equals boiling point. This is negative 0.5 degrees Celsius. We add 1 carbon to that, which will increase the number of interactions between molecules. And the BP now is 36 degrees Celsius. And I'm going to add 1 more carbon to make hexane. And my boiling point now increases to 69 degrees Celsius. So as we increase surface area, or contact in the surface area, this will increase the boiling point. So if you think of another molecule of butane stacking on top of there, some of those can stack together and make negative 0.5. They have 4 different contact points with those carbons. And then if we increase the contact points with pentane, that's going to increase our boiling point. And now with hexane, we have even more stacking and more boiling points. So that's going to increase the surface area contact, and that increases then the boiling point. The boiling point is also affected by the shape of the compound. So all of these isomers you can see here have the same number of carbons, but their shape is a little bit different. So the shape of these is different. The boiling point for this straight chained hexane, so the boiling point here for this flat hexane is 69 degrees. If we add a methyl group and then cut off one of those carbons to move it to the middle, this boiling point is 63. Then we have 60, 58, and 50. So as the overall shape of the molecule becomes less linear, our boiling point decreases. So if you think of how this can stack, if you drew the overall shape, it's kind of flat. So if you had a bunch of those Legos that stacked like this, there's a lot of surface contact with each of those. And as we add methyl groups to different locations, the stacking ability is not as great because even though I can stack here, this has got this kind of pivot point in here, and the overall shape as we get down to here is more spherical-like, so there's less surface contact. So then our boiling point is going to decrease. So we know that water has a boiling point of 100 degrees Celsius. Which is pretty high compared to these hexanes. So that hexane that is straight is 69 degrees Celsius, but water can hydrogen bond. Hydrogen bonding is an intermolecular interaction that is very strong, and they associate well together. An H from the water can hydrogen bond to another oxygen, and likewise there. So this could hydrogen bond to another molecule of water. So these are stronger interactions, and so they have more surface contact, and you're going to have a higher boiling point that we see with water. So if we're answering questions about pentane, which has 5 carbons, heptane has 7, decane has 10, which one has the highest boiling point? Well, decane has the most carbons, so that one will have the highest. The one with the lowest boiling point is going to have the least number of carbons, so that is pentane. Then we're asked here why Vaseline, which is a complex mixture of hydrocarbons, is used as a skin lubricant and ointment. It's insoluble in water and soluble in dichloromethane. So if it's just hydrocarbons, it's not water soluble because there are no oxygens. So we get that from it being a hydrocarbon, which if you're using it to keep moisture in, the lubricant is not water soluble, so moisture can't get in, but it also can't get out. But it is soluble in dichloromethane because this is an organic solvent and dissolves like. Alkanes have no functional groups and are not very reactive. A couple of reactions that they can undergo include oxidation, which results in an increase in the number of CO bonds or a decrease in the number of CH bonds. Okay, so if you remember oil rig from general chemistry, we can use that here. So oxidation is loss of CH bonds. Or it can be the gain of CO. Reduction is the gain of CH bonds. Or loss of CO. In a combustion reaction, we burn the carbons in the presence of oxygen to make carbon dioxide and water. So carbon dioxide plus water. In methane, we have CH4, that's the formula for methane. We're going to burn it in the presence of oxygen, which requires 2 molecules of oxygen to make CO2 plus water. That also gives off energy. And with these types of equations, we want to make sure to balance the equation. So I have 1 carbon on each side. My oxygen molecules are not balanced. I have a CO2 here and then 1 oxygen here. So to balance that out, I have 2 from the CO2. I have 4 total, so I need 2 H2O, which also balances out my hydrogen. For isooctane, which is a high octane component of gasoline, we add a flame to that. I'm going to get CO2 again. The products of these combustion reactions are always carbon dioxide and water. But the stoichiometric ratio is going to change. So for this one, If you go through and balance it, we'll need 16 carbon dioxide plus 18 water in order to balance that out. Yeah, when we're combusting alkanes, natural gas, or gasoline that's used in heating, this is going to release energy, and this energy can be used to heat homes, to power our vehicles, or to cook our food. Unfortunately, because we are creating carbon dioxide, this is a greenhouse gas that absorbs thermal energy and redirects to the surface. And overall, it's going to increase the average temperature of Earth's atmosphere. So we get this global warming effect with all this carbon dioxide that is undergoing combustion. So you can see how the amount of carbon dioxide concentration has changed from 1960 to not quite 2020. Driving a car 10,000 miles at 25 miles per gallon actually releases 10,000 pounds of carbon dioxide into the atmosphere. So here's a couple of problems for balancing the equation. I have propane plus O2. My product is CO2 plus water. On the left side, I have 3 carbons. So I need to add a 3 here. So that balances out my carbons. Just make a note of that here. I'm going to do my hydrogens next, actually. That will be the next easy one to do. So hydrogens, I have 3, 6, 7, 8. So I need a 4 here. So then if I tally up my oxygens, I have 4 plus 6, so 10O. And I can just put a 5 in front of here to balance that out. For butane, the product is the same. 4 carbons. I have 10 hydrogens, so I'll put 5 out here. 13O. So what you can do is do 6.5 O2, which is half of 13, or you can just multiply everything times 2. So this would be 2, this is 13, 8, and 10. Incomplete combustion can result in carbon monoxide. So if your gas doesn't combust cleanly, we can also get the introduction of carbon monoxide, or CO. Plus 4 waters and energy. This is a poison gas that can bind to hemoglobin. This can reduce the amount of oxygen that's transported into your bloodstream, and this can also be formed when cigarettes burn. When wood is burned in a poorly ventilated fireplace in a well-insulated room, the carbon monoxide concentration can reach an unhealthy level, so you want to make sure if you're burning wood in a building that it's well ventilated. One other reaction that we can do with alkanes is halogenation. And here an alkane reacts with chlorine or bromine to form an alkyl halide. So this halogenation reaction, we have an alkane with the CH. We add XX with light or heat. And we introduce the halogen here, plus HX. So these you can think of them as swapping places. If you have methane, this is just going to swap places here. And these aren't the arrows that we're actually using. It's just so you can kind of get an idea of what's happening. So I'll get Cl plus HCl here. And then with ethane, I add bromine. And the Br will take the place of one of the bromines. And we get HBr. So this is the alkyl halide. We have 1 chlorine here. This is chloromethane. And this is bromoethane. In a substitution reaction, or which is what we've been doing, this is a reaction where an atom is replaced by another atom or group of atoms. So this hydrogen is going to get replaced by the Br. And we also form H, Br in the process. So that is the substitution of H by Br. And in the case of this compound here, I'm just going to draw out the stick structure here. So this is what it looked like before. So in this reaction, the bromine is going to replace one of the hydrogens here. So we'll just add a bromine there. And this is the skeletal drawing, so you don't have to include the hydrogens, which is why they weren't included here. For this problem, the reaction of butane with chlorine in the presence of light forms two different alkyl chlorides that have the same molecular formula of C4H9Cl. Draw the structures of both alkyl chlorides. Butane is a 4-carbon chain, which looks like this. We're going to react it with chlorine in the presence of light, which can also be written as HNu. And chlorine can be replaced on the end. It can take the place of one of these hydrogens here. Or it can replace one of these hydrogens here on the second carbon to give us this compound. Both of these have the formula C4H9Cl. The last problem here, what alkane is needed as a starting material to prepare the following by a halogenation reaction? The halogen that we need is chlorine. We're going to be adding chlorine here. So this will be Cl2 plus light. And in a halogenation reaction, we're replacing chlorine with a hydrogen. So before we'll just have had cyclopentane.